Hello there, welcome to my channel on chemistry lessons. This channel provides full lesson content and full lesson videos on all chemistry topics for AQA, A-level chemistry and BTEC applied science. I will be uploading regular content. Initially it'll be full lesson content, and as we get closer to the exams I'm going to be looking at focusing on key concepts and exam technique. So please subscribe so you don't miss out on future content, and also use the comments features to let me know what you think of the videos and any future videos you think would be useful. Good luck. So this video is the final lesson in the A2 electrode potentials topic and focuses on the commercial applications such as batteries and fuel cells. Okay, so before we go on to look at batteries and fuel cells, let's have a practice of the content so far, because batteries and fuel cells is just application of what we already know. So I want you to pause the video and have a go at this question. And when you're ready to go through it, unpause the video. Right, okay, so the standard reference electrode, that's the hydrogen electrode. So it's the standard hydrogen electrode, or you can just call it the hydrogen electrode. B, what is the function of the platinum electrode? Well, in this case, this half cell doesn't have a metal electrode, therefore platinum electrode is used. The platinum electrode, what it does is it allows or gives a surface for electron transfer to take place. So it's to allow electron transfer, or it provides a surface for electron transfer to take place. What are the conditions then? So the conditions to measure the Fe3 plus, Fe2 plus, all solutions, now don't just say all solutions, we're going to actually identify the solution. So Fe3 plus, Fe2 plus, and don't forget this H plus, because in order to measure the potential for Fe3 plus, Fe2 plus, you're going to have to compare it to a hydrogen electrode. So all three solutions here must be 1 mole per decimeters cubed. Hydrogen gas must be 1 atmosphere, and the temperature must be 298 kelvins. Okay, C. So the EMF, it's the right hand side, take away the left hand side. So in this case it's this electrode on the right, which is 1.51, and the left hand electrode is the one at the bottom, so minus 0.17. That comes out at plus 1.34 volts. I'm going to have to make sure I give units here. Okay, now the equation is quite a complex one. So we're looking at this one and this one. So this is the negative electrode and it's oxidized. This is the positive electrode and it's reduced. But if we look at the electrons, we need to multiply the top one by 2 and the bottom one by 5, and then we can combine them. Right, so it's got to look like 5H2SO3 plus 5H2O plus 2MnO4 minus plus 16H plus, and then the electrons have cancelled. Goes to 2Mn2 plus 8H2O plus 20H plus 5SO4 2 minus. Now that's not the correct answer, because I can simplify this. I've got water on both sides, so I'm going to remove, I've got 8 water on the right, 5 water on the left, so I'm going to remove all 5 waters on the left and just end up with 3 on the right. So I've taken 5 waters from both sides. Likewise, I've got 16H plus on the left, I can get rid of all 16 of those, and take 16 away from 20 is 4. And that is my correct answer right there. So 5H2SO3 plus 2MnO4 minus goes to 2Mn2 plus 3H2O plus 4H plus 5SO4 2 minus. You must simplify down if you have the same species on both sides. identifying the strongest oxidizing agent. So the strongest oxidizing agent is the thing that will gain electrons the easiest. So the one with the highest electrode potential, in this case it's Ce4 plus aqueous. I'm looking for the largest value, which is 1.7, and then I go, there it is. So which of the species could convert Fe2 plus into Fe3 plus? So it could do this, but could not convert Mn2 plus. So it has to be one of these two. So we've actually got a choice here. Okay, so it could be Cl2 gas, or it could be VO2 plus, which requires to be acidified. And finally, so I'm looking for a cell EMF of 0.93, so I'm looking for a difference of 0.93. Take a little bit of working out, but you will find that the difference between the ion 2 and ion 3, and it's the top one, so the difference between these two here is plus 0.93. So then what we need to do is combine these two, or do a cell representation anyway. Positive electrode goes on the right, in this case it's Ce, and we always put the most oxidized form closer to the salt bridge, and they're the same phase, so they're separated by a comma. Now because they're both solution, we require a platinum electrode, and the negative electrode is our iron, so the most oxidized form closest to the salt bridge. Again, they're both solutions, so they're separated by a comma. Then we need a platinum electrode in that case as well. Right, so let's look at the spec for this final topic of electrode potential then. So there's no new chemistry here, it's just application of what we've already learned with electrode potentials. So we're going to look at what batteries and fuel cells are. Okay, so it's the chemistry of batteries and the chemistry of fuel cells. Okay, so batteries, that's just, it is using electrochemical cells. It's using them as a commercial source of electrical energy. We use batteries everyday life. And the EMF is the voltage of the battery. Batteries can have different voltages. Now, the kind of batteries that you put in kids' toys, usually the EMF or the voltage is around about 1.5 volts. Obviously, you can get 12 volts, you can get 24 volt batteries for kind of power tools and things, but the EMF is literally the voltage of the battery. Two main types of batteries then, non-rechargeable and rechargeable. Okay, rechargeable are far more common now, and it's becoming a big business, rechargeable batteries. Right, so let's start by looking at some non-rechargeable then. They're most commonly alkaline batteries, or what we call dry cells. They're literally used once and then they are discarded. And sometimes people refer to them as a primary cell. And there we go, that's a cross section of a non-rechargeable battery. You'll probably recognise that you've got the positive at the top, so this would be your positive electrode, and you've got the negative electrode. So the positive electrode is literally what you can't see. The positive electrode is going right through the centre of the battery. There's like a rod, so here they're using a carbon rod, and the outer lining of the battery is also metal, and that's the other electrode, and in this case it's a zinc battery. There's a zinc paste in there, so you can see you've got zinc in two different oxidation states, and then we've got a manganese paste in there as well. Now the good news is you're not expected to memorize and learn all the different bits of a battery. Okay, you just need to be, you'll be given data and you need to work out and use the data, kind of what we've been doing in previous lessons on this topic. So there we go, there's the two half equations, or the two half cells anyway. There's a zinc and a manganese. What I want you to do, I want you to pause the video and you're going to see if you can construct, well, there's three questions. So you're going to construct the cell reaction and predict voltage, use oxidation numbers to predict or to say what's been oxidized and reduced, and then kind of an extension one if you like, why do you think old discharge batteries often leak, because if you leave batteries in things like this type of battery, generally when you come back to it after a year or two, they've leaked. Every year with the Christmas decorations for me. But pause the video and have a go at these three. Right, cell reaction then. So in this case, the zinc is going to be the negative electrode and will be oxidized, and the Mn is going to be our positive electrode because of the values here. Right, okay. So the cell reaction, we will need to multiply the top one by 2, so it'll be Zn plus 2Mn or 2 plus 2H2O equals 2MnO plus 2OH minus plus Zn2 plus. Can I cancel it, simplify it? No, I can't, so it's a final answer. And predict the voltage, it's 0.74 minus 0.76. So this is a 1.5 volt battery. Using oxidation states. Right, well, we can see, hopefully fairly swiftly, that the zinc has been oxidized. So zinc has been oxidized, and it looks like the Mn is going to have been reduced, but let's have a look. It's +4 here, and over here it's +2. Yes, so manganese has been reduced from +4 to +2. And finally, why do you think old discharged batteries often leak? Well, look what's happening. The zinc is being oxidized to Zn2+. So this outer casing of the battery is actually going to get thinner and thinner as the battery is used up. So as the cell reaction takes place, this zinc is going to get worn away, and it becomes weaker. So it's more susceptible to leaking. Okay, next then, again, I'd like you to pause it and have a go at this one yourself first. And then when you're ready, unpause it and we'll go through it. Okay, so now we've got another non-rechargeable battery. And you'll always be supplied the data here. You're not expected to memorize or know any of this data yourself. You will be given it in the question. Right, so cell notation for the cell used to represent the zinc silver. Okay, so the negative electrode is going to be Zn, so we'll put that on the left. So we'll have salt bridge, Zn, phase boundary, there we go. And on the right hand side we've got the silver electrode, there we go. Positive electrode being on the right hand side, negative electrode being on the left hand side. Half equation forms at the negative electrode, so the negative electrode, the half equation for the negative electrode, Zn goes to, it's as simple as that. It's just the reverse reaction of the negative. It's the negative electrode there, the oxidation being shown. EMF of the cell, 0.34 minus 0.76, 1.10 volts. And write an overall equation for when the cell is discharging. So we're going to have to combine the two half equations here. Don't need to multiply them through. We can just go Zn plus Ag2O plus 2H plus goes to Zn2 plus 2Ag plus H2O. Any simplifying? No. Done. Check the answers there. Okay then, so moving on to look at some rechargeable cells. Massive advantage over non-rechargeable because you can use them many times. And often we call them secondary cells. Most common types are nickel cadmium and lithium ion. Particularly lithium ion has kind of really taken off over the last few years. So this would be classed as a nickel cadmium. You can see the two half equations. One contains cadmium, one contains nickel. Again, we don't need to know the structure of these batteries. We just need to be able to use the data if we are given it. So, task here then, see if you can construct a cell reaction for that battery, predict the voltage, and again, using oxidation states to show what's been oxidized and what's been reduced. When you're ready, unpause your video. Okay, so cell reaction, the cadmium is going to be the negative electrode. We need to multiply the positive electrode by 2 because there's only one electron there. So it's going to be Cd plus 2OH minus plus 2NiOOH plus 2H2O running out of space. Can anything cancel? Yes, it can. And there we go. Predicts voltage, positive electrode, take away negative electrode. There we go. Calculator. .4 volts. Oxidation numbers, well, in cadmium from 0 to +2, so cadmium has been oxidized. Nickel, slightly more difficult, this one actually. Nickel, we've got the OH, which is a minus, so it's plus, so nickel is +3 on the left, and on the right it's +2. It's been reduced, so nickel has been reduced. Okay, let's look at a lead acid cell then. So again, you don't need to know these equations, you will be given them in the exam. Okay, this is a lead acid cell which is used in cars. You find that a big car battery is a lead acid battery. So here I want you to again look at the cell reaction for the battery, predict the voltage and use oxidation numbers. So pause the video and when you're ready to go over it, unpause it. Okay, cell reaction then. So this is our negative electrode. This will be reversed. It'll be oxidized. This is the positive electrode. It'll be reduced. Thankfully, the electrons already cancel. There's 2 electrons in both cases, so I don't need to do any multiplying. But it is going to be quite a long PB. I'm not going to put state symbols in just to speed this up. However, I would advise that you do put state symbols in. I'm just copying it down, that's all I'm doing, but showing the oxidation and the reduction. That's going to go to PbSO4 plus 2H2O plus PbSO4 plus H plus. Now look out for things to cancel. Usually there's some waters or some H pluses or OH minuses that can cancel. And there we go, I can get rid of this H plus and this 3 can become a 2H plus. Now the cell EMF or the voltage will be 1.69 minus 0.46. So it's the positive electrode, take away the negative electrode. 1.69 minus 0.46, 1.23 volts. And what's been oxidized and what's been reduced? Well, the lead is 0 over here, and over here the lead is +2. So the lead has been oxidized. And what's been reduced? And you've also got lead on the left, look, as +4. and it's also +2, so the lead is being both oxidized and reduced here. So the lead is being oxidized and it's being reduced. Okay, so that's the end of that lesson on batteries. Okay, next lesson we'll be looking at fuel cells, which is very closely linked, so look out for that video. Good luck, hope it was useful.